Okay, next we will talk about port level interface protocol. Right, I have to speak faster. Yeah. Basically, the port level interface is used to transfer the data, and the argument of a function has the following type: either pass by value scalar, or pass by reference array, or pointers. Yeah. And this port level protocol, suppose you have a two kernel function to connect back to back. Then those port level protocol suppose you to connect this module directly without further interface in between. Okay. Yeah. So for example, you have an adder. Okay, and then the adder will generate output value. Remember, the output also come with the port level protocol AP down. Or, okay, then this interface can connect to the downstream. Okay, downstream, if we use the AP value protocol, okay, the AP down signal provide the value signal for the downstream module to sample the data. Yeah. So those port level protocol are very primitive and easy for you to connect the module back to back together without adding the interface circuits. So let's look at the port level interface protocol. They are very, very simple. Yeah, first, no IO protocol. That's an AP none. Okay, so for AP none, it's a purely wire. So it has only the data port and no additional control signal. Yeah, so that's a AP now. Or AP stable, that means the input actually is a configuration. So input doesn't change after the reset. Yeah. And so for AP stable, then there's no need to register the port fan out. It's because it's static signal. The signal does not transition. So no matter how much external fan out is, there's no need to add a register to pipeline that, yeah, because it's a static signal. Okay, the handshake, AP handshake. Basically, there are two signals, AP value. The control signal include AP value and AP ACK. Okay, AP value means indicate the data signal is valid. AP ACK indicate the data has been received. Yeah. So the protocol is very simple. Yeah. So for the upstream module provide the data, then you assert the data and also the valid signal. And for the downstream receiving the data, once it's received, then you assert the ACK. So it's a valid ACK signal as a pair. In the following example, yeah. So if there is no ACK, then the input has to hold, extend the input data until the ACK assert, then you can change the data. A very, very simple protocol. Yeah. So the handshake, so passed by value, then AP value, AP ACK, yeah. So this is the IP level protocol. As we said that you can have an adapter, right? Convert to XI like. Yeah. So the AP value will be used for the enable signal for the register, and that's the data. Yeah. Okay, so then you latch the data and then can read for the host. Yeah. So you can see for those interface signal, it's easy to convert to XI interface. Okay. So for the memory interface protocol, basically it's for array argument. Its default is using the AP memory. So for access the memory, you need the following signal address and enable or chip enable. Okay, that's for read. Okay. Then if for write, then you can have you need additional control signal write enable. Yeah. Okay. So in this example, the y, okay, the argument y actually is bidirectional. You read the y memory and then you write to the y memory. Yeah, and you generate the interface signal write enable and chip enable. Okay, and you can make this signal as a two-pole memory too, so that you can do these things in one cycle. Yeah, you read it out and then pipeline right to next. Yeah, so you can have if you provide two-pole memory, then you can do the II equal 1 pipeline for this loop. Yeah, because for each loop you need to read the Y array and also write to the Y array. Yeah. And FPGA provide two-pole memory. Yeah, allows you to do these things. And for the memory interface, you need to remember that for read, okay, it takes one cycle latency, and for write, okay, you need to provide the address and the write data at the same time. Yeah. So that's a very simple memory interface protocol. Okay. So for the memory interface, if you use the BT's AAHLS-NTU, then you can specify either AP memory or block run or APFIFO for the array arguments. And the difference between AP memory and BRAM is AP memory is for general memory interface. So you will see a lot of memory interface signal like chip enable, write enable. Yeah. But if it's a block using the block run, then all those interface aggregate. If you look at the IP icon, you will see the interface. Actually, they bundle into a single port. Yeah. Okay. So for the APFIFO, the HLS will detect your code and find out if it's a sequential access. Then you will try to use the APFIFO. And the benefit to use the APFIFO is it doesn't need to provide address. So you save the logic for the address generation. Yeah. For memory, you see, you have the address. So that needs certain logic to generate the address. Okay. For example, like a counter, yeah. You increment the address. Yeah. Then using the FIFO, then you save the address generation logic. Okay, here talk about the APFIFO. Yeah. So in order to use APFIFO, then this array has to access always continuously and also in one direction. So for this variable, it's either input or output. It cannot be input and output. Okay. So if you satisfy these two conditions, then you can use the APFIFO. Yeah. So it's area efficient and no address generation logic. Yeah. And for the interface signal, in addition to the data port, they need two control signal. One is for input, that's an input empty signal. You can think the input empty map to the valid signal. Yeah, if it's valid, then you can sample data. Once you sample data, you output X. So that's corresponding to FIFO is you can think that that's a pop signal for the FIFO. And for the output, that you assert the data, and also if its output is full, then you cannot change your output data. Yeah, you can see the right corresponding to push signal for the FIFO. Yeah, so that's the basic protocol. For input, if it's not empty, because this signal is active low. Yeah, when it's high, that means not empty. If it's not empty, then you can assert the in ready. That means I already read the input, so the input can change into next value. Yeah. And for output, like in this case, since the output is full, it's not full. High is not full. If you actually output the data, but since the output is full, then you cannot pop. You cannot pop. So you have to keep the output data until you find out the output is not full. Then you can assert the pop or the output right, and then you can change the output value. Yeah. So that's a very simple FIFO interface protocol. Okay, so for the port level protocol, it's quite simple, and let's talk about the XI interface. Yeah, basically there are three: XI lite, XI master, and XI stream. Oh, okay. Again, we have seen this diagram before. Yeah. So it needs a adapter circuit to convert the port level protocol interface signal into the XI interface. Yeah, when you are doing the IP integrator. Yeah. XI light. Okay. Yeah. So this so-called adapter. This adapter module. Yeah. For the module, for example, like this one. Look at the code. Yeah. It has A, B, C, and the A and B are Q input, and C is I/O. Okay, and for the port level, for the block level is XI light. Okay, so the block level protocol is specify address 00 to 0F, 16 byte, 16 byte allocate for the back level protocol. That include the AP star, those stuff. Yeah. And so it also indicate that's a handshake, AP control handshake protocol. So that means that include the AP star, AP down, AP ready, those signals. Yeah. And then for the data port, it also has a XI light. That means all the data argument is passed through the XI light interface. Yeah. Okay, so in that case, in your C code, you use a pragma to specify the argument ABC is a XI light. That means those arguments pass through the XI light configuration. Yeah. Okay. So the adapter circuit that will map those ports at a specific register address. Okay. Yeah. So this pretty much we covered that already. Okay. So So for XI Lite, when it's associated with block level protocol, so you use the port return. Use this return port to specify block level protocol. So in here is a XI Lite. So this is the default block level protocol. And for block level protocol, you can also associate using the AP control HS. You can also use AP control chain, right? Yeah. That means if you use the AP control chain, that will have additional AP continue uh, signal of the register. Yeah. So block level by default using XI Lite, and further you specify is APHS. That means a single kernel function, non-pipeline. And if you want to do the pipeline, you specify here AP control chain. Yeah. And the block level protocol, those interface signal is defined at this address position. In particular, like B0 contain the AP start, B1 is AP down, B3 is AP ready, and B2 for AP idle. Yeah. And for AP control chain, it contains the AP continue. Okay, so I think everybody is very clear about it. Okay, this further address in more details that there are 3 ports. For example, for the port A is that's a port B. Port B specify output. Port B is output. There's a AP value. That's the input specify protocol AP value. So once you specify AP value, then it contains another control signal AP value. Okay, like a port A is a AP control A port. It doesn't specify, so by default it's AP none. Okay, it's the AP noun that it has a very simple data port. It doesn't have an additional control signal. Yeah, and for port C, it's a bidirectional signal, so it contains the input and the output. And for the output, as we see that the default is all valid protocol, AP all valid protocol. So it has an additional control signal indicate the output valid signal. Yeah. Okay. So in here it matches uh, the whole the table. Yeah. The default protocol is used. Okay. Let's talk about XI master. Yeah. Okay. When using the XI master, we use the XI master transfer block of data. Yeah. So when you transfer volume of data, you want to make sure it's efficient. Yeah. And those assets goes to the DRAM. And DRAM, when you access DRAM, unfortunately, we didn't talk about the DRAM interface. The DRAM interface we will talking in the FPGA lecture. Yeah. And you will know to use the DRAM, in order to have a higher utilization on the DRAM bus, you like to use the burst access. Because if it's not burst, because it takes a longer latency to access the data. If you just access a very small amount of data, then you can imagine the DRAM bus utilization will be very low. Yeah. So in here, okay, that's a pointer. Okay, let's look at this code. For this code, you will see that there's a no loop. There's no loop here. So that's only single access, single read, and single write. Right? You read a single 32-bit data, and later on write 32-bit data. So if you write the code in this way, then the DRAM will be very inefficient. Yeah. Okay. So for the XI master, we use for pointer and array argument. Yeah. And the default alignment set to 64 byte. Yeah. And the rewrite burst up to set to 16 by default. That's by default. Yeah. So we will already talk about the single transfer. Let's talk about burst transfer. So we like to do the XI master in burst transfer mode. There are two ways to do that. One is using a memory copy. Let's look at this example. Okay, in here, that's a pointer A array. You specify this port A is a master interface. Okay, and you also need to have a XI light because XI light specify the base address for the XI master SS. So in here, that's the basic read, and then this one is the compute. And right, that's a typical kernel function. You read the input and do the compute and write the output. For the read, you use a memory copy. So memory copy will provide the burst access to the memory. In here, that try to read the memory array from A to the internal memory buffer here. It defines here. And you read 50 of a 4 byte. Yeah. And then you do the computation, and then you write out. When you write out in here, it doesn't use the memory copy. It uses a for loop, using for loop, and with a pipeline. That's important. That's the way you generate XI master. Follow exactly this coding style. Okay. So for burst transfer, either you use a memory copy or you use a for loop with pipeline. Okay. And when you write the for loop, you have to take care of the following things. First, you have to pipeline using this pipeline pragma. And the address must be in increasing order. Okay. In here, the I here is actually it's not the address because it has a base address and then it just increment. So for this loop index has to be increment. If I use a decrement, for example, I equal 50, yeah, and I greater than 0 and I minus. If you write this way, then the HLS will have a hard time, cannot generate the burst SS. Also, don't put the SS inside a conditional statement because burst SS, you cannot have a conditional. Say, I want to read this address and not read in next loop. Yeah. So, so the HLS when it detect there is a conditional access, then you cannot do the burst. And also, if you have a nested loop, okay, you have a nested loop, do not flatten the loop. Because once you flatten the loop, the sequence of access the memory will be random or no guarantee. Yeah. So don't flatten the loop. Also, only one read and one write allowed for the for loop. Yeah. And that's the port. For example, if I have a for loop, okay, and then you read the memory and write the memory, and these two memory target at the same memory port. So, for example, this is the same memory port. Then read and write, so that you cannot do the burst. Okay. Unless I read a variable is in memory channel 0 and write another variable, and that variable is assigned to memory channel 1. In that case, you can put into one loop. with a rewrite because they target to different memory port. Then it can still do the burst. Okay, so remember those rules when you write the burst access in your C code. Okay, so in here we need to have a system view about it. Yeah. So for the kernel interface, that once you put the adapter, it becomes the master, XI master. Yeah. Okay. So when you look at the system view, you will see that this XI master cycle goes through the XI interconnect and goes to the memory controller and finally reach to DDR memory. Yeah. And this one takes a very long latency. So how long is this latency? You don't know. It depends on the system. And also the latency actually is varied. The latency is not a fixed constant because there are multiple as master access the same DRAM. So the DRAM controller will do the arbitration to access the DRAM. And this arbitration create the access latency uncertain. Okay. However, you need to have an idea about the average latency. So when an engineer design the system, you need to have an idea what is the average latency. Also, you want to know what is the maximum latency. The maximum latency could be very long when the system is very congested and you have a lower priority. You may wait for a long time in order for your turn to get to access the data. So when you do the design, what we did before is we will have a software engineer write the code. Okay, for example, the software engineer write the code for the PS running on the ARM processor. He simply write the code through a loop to read the memory, and then he run many times and to calculate the latency. And then you try to draw a histogram. Then he will know the distribution of the latency. And then it will decide his application, what is the maximum tolerance you can delay. Yeah. Then it design the appropriate system architecture to address the long latency. Yeah. For us to design the hardware IP embedded in the system, then we will also write a test module. Okay, the test module just doing the loop to read the memory or write the memory, or do the rewrite, or generate all different traffic, and then you try to measure the latency. Yeah, of course you recall those latency and draw the histogram. Then you will have an idea how much latency for this particular system. So you have to run the system in a realistic application. You don't want to write to measure the DRAM latency for a single kernel. Yeah, if a single kernel, no, that's not realistic because in the real system there are multiple kernels running. Yeah, so you have to measure the latency in as much realistic as possible in the actual system. Yeah, then you measure the latency, and that latency is very important to decide your design. I will talk about that later. Yeah. Okay, so when you use the XI master, it provides several options. Yeah. You can specify the depth. The depth is simply for you to do the test bench testing. Yeah. This one specify when you do the test bench how much buffer you allocate to do this test. Why you want to use the depth? For certain kernel function, if you define your array with certain size of array, there's no problem. Yeah. If there's a pointer, if your argument is a pointer, in this case, that when you do the simulation, code simulation, you don't know how much vector the input test data you need to create the buffer for it. So basically, you use the depth information to tell, because when you do the cosim, it generates the test bench. Okay, when you do the test bench, remember in last week we talked about the test bench, you do the cosim, you have the C code, the host program, and you have your kernel function. And the kernel output, you will do the post-processing. So when you do the C program to prepare the input test data, you want to know how much test data need to prepare to feed into the kernel, because the kernel run in the Verilog simulator. When you run the Verilog simulator, all the test data has to be available, right? Yeah. So you do need to know the depth of the input data to run the Verilog simulation, and this depth provide the information that here. Yeah. So this depth basically tell the tool to allocate that much buffer in order to do the Verilog simulation. Yeah. So I think some of you may experience that when you run the code sim, that system hang. Okay. Most of the time is due to the depth is not deep enough. So that uh, when you run the Verilog simulation, they cannot get enough input data. So the Verilog simulation simply hang. Yeah. Okay. So that explains the use of depth. And the latency is also, you specify this part of latency. Yeah, this one, it gives you a ballpark number for the system latency. Actually, I think those latency is too aggressive. In the real system, I will see a much longer time. Yeah. Okay, the following two argument option will affect the actual hardware resource allocated. The first two doesn't affect the hardware resource. It's only for simulation purpose. Yeah. The next two is important. The first one is the maximum read burst length. That means when you do a request, that's basically that's a for loop. Okay, the for loop you specify how many iterations, and that number of iterations that specify the read burst. Yeah. Okay, specify the maximum number of data value read. Another option is the number of read outstanding. I will explain this. Yeah. Specify how many read requests can be made to the XI burst. Yeah. So so the XI master for read cycle, you need to be able to hold a certain amount of data for the data return. That is determined by number of read outstanding times the read burst length and the word size. So if you specify those numbers, it will allocate the read data buffers with that much amount. Okay, because when you first read come back, that you have to hold those data. Okay, here I want to give a more detailed explanation on the latency and bus utilization. Okay, let's say that you have a single transfer. So you generate a request, you generate a read request, and the data take certain time and return. Okay, so that's the latency here. You specify the latency here. Okay, let's say the latency is 100 cycle. Okay, so you can imagine, and you only get a single read data, single one piece of the data. Then when the data comes in back, and at this case, the number of outstanding equal 1. And burst, there's no burst. Okay. So when you can read the next data, when the data come back, then you generate another request. And then you generate another piece of data. Okay. In that case, you will see the DRAM bus utilization will be very low, right? Yeah. Will be very low. That's the utilization only maybe 1%. Your latency 100 T and you only transfer one cycle of data. Okay, so DRAM bus is it's low. So how can you improve the bus utilization? So first, you want to use the bus transfer. Okay, but bus transfer, there's a limitation. Yeah, maybe, I don't know, maybe you said bus that's 16. Okay, so in that case, that you take 100 cycle to get the first data, and the data will transfer for 16 cycle. And then you have another request. Yeah. So in this case, what is the bus utilization? Yeah. So that means 100 plus 16 over 16. Yeah, that's your bus utilization. Okay. So bus transfer do increase your increase the bus utilization, but it's not enough. Then you come again the number of outstanding. So that means the first request 1, and then after 100 cycles, start doing the 60 cycle of transfer. Okay. So number of outstanding, if you put another one here. Okay. Then if it's back to back, you continue back to back. Yeah. So you can continue 16 cycle transfer. Yeah. From here, there's another. Yeah. Yeah. So this in this case, the outstanding equal 2. Is the outstanding equal 2 enough? If I want to get 100% bus utilization, what is the minimum number of outstanding? Yeah, just a roughly number. You can always put big number, right? The big number maybe too much overhead and not necessary. Yeah. Yeah. So you can see that 16 cycle and latency is 100. Yeah. So maybe I can have a 5. Yeah, 100 to 16. So that means for next request comes in that this request that's 100 cycle come out. So how many 16 cycle in 100 cycle? It's about 5 to 6. So maybe you choose the outstanding 6. Or it's probably 6. Yeah, that's 6 or 7. Yeah, to 6 or 7. In that case, in this case, then you can fully utilize the data bus without idle time. Yeah. So do you understand? remember, you don't want to put, for this number, you have to use wisely, because these two number that determine the FIFO size, right? Yeah. If you too big a number, it's not gain you anything, that you simply create useless waste of the resource. Yeah, so need to calculate. Also, as I said, that the latency is it's not constant number. It depends on the system traffic. So you have a histogram. You will know in average, or maybe 90% of the time, the latency is less than 100, for example. Then the system designer have to judge whether that kind of memory throughput is good enough to meet the system requirement. Yeah, so don't over design it. Yeah, so this gives you a guideline how to specify the burst length and the maximum number of outstanding. Yeah. Okay. So okay, the XI bundle, that means right now in the U50 has using the HBM. Okay, what I'm talking now is in the introduction to FPGA. Yeah, you may not understand what I'm saying. In the U15 FPGA use HBM, and HBM it provides 32 memory channel. Okay, and for other DDR memory, if the FPGA is use DDR memory, it provides 4 port or sometimes 6 ports for the memory interface. But that's FPGA specific. You have to know what FPGA you are using. That means I have a 4 or 6 memory controller, and each memory controller control one memory channel. Yeah, and if you want to design high performance system, that you want to fully utilize those memory channels. Yeah. In that case, especially for AI application, we all know that for AI, the performance bottleneck is the memory throughput. Yeah. So definitely you want to fully utilize the memory channel. So in that case, I can assign those variable in different channel, so that give you a higher throughput. So in this case, I have 3 arguments, 2 input, input 1, input 2, and 1 output. And in this example, I all assign to the bus A. Okay, that means I only use 1 memory channel here. There's only 1 adapter to the memory controller using 1 XI channel. Or I can use distribute using more memory bandwidth by assign. For example, in here, I assign the input 2 as a bus B using another memory channel. Okay, so right now I have in 2. Okay, that's 1 memory channel, and in 1 and out using 1 memory channel. Then I have a 2 XI interface to the global memory IP. Yeah. In this case, you increase the memory throughput. Okay, so that's one thing that you can use to increase your memory throughput. Okay, next we talk about APFifo string interface. Yeah. String interface, you can think it's FIFO. Yeah. So FIFO, that means you have one producer and one consumer. That's FIFO. Okay, that's a basic stream. You just think that's a FIFO. So you will see that's only one direction. So you cannot support two direction. So array and pointer can use string, but make sure the array is either input only or output only, or pointer. Yeah, we know pointer can be very flexible. It can be read from, you can also return to. Yeah, just make sure your code is written that only used for one direction. In that case, you can use the XI string. Yeah, and mostly we use the data flow between functions. And data flow we will explain in next lectures. And multiple variable you can group into a single string. For example, I have a variable is defined as a struct, and they have a multiple member variables, and that can be grouped together using one string. Yeah. So for string interface, that's a typical usage. You have a string input, and for each kernel function, use a string in, string out to pipeline. And this data flow is more efficient than the pipeline. Okay. As I said, pipeline, you need a pipeline state machine. So that's a control-driven architecture. And for data flow, that's data-driven control. That means the next function can start execute when there is a data appear in the FIFO. It can start right away. It doesn't need to wait for the previous function complete. Okay, if it's pipeline, you have to finish this and then start this one and start this one. Okay, that's the pipeline. Okay, and then for data flow, once it produces the data and the data FIFO is not empty, then this one can start. So using the data flow gives you shorter latency. Okay, so we will see that for system level design, all those multiple kernel, we most use string interface between those kernel functions. We use it a lot. Okay, so XIX that uses string interface. That's a XI4 string protocol. For this protocol, you have a typical signal is the data and T-last. T-last that means for this string, the end of the string, and you use the T-value to start the string transfer. Okay, so you assert the T-value. At the same time, you put the data and T-last, put the data on the string interface. And then you can continue send the data and last. If the last assert, that means that's the end of the string. Okay. If you want to start next string, that you assert the T-value again. So the protocol is very simple. Yeah. Once you have a data to transfer, then you assert the T-value. And then the downstream consumer can start processing. Yeah. And the AAHLS provide the a template with the XIS. So in addition to the data and the last, okay, it also has other so-called side channel signal. Side channel signal. Okay. For example, the keep you can think is a byte enable. You have a multiple byte to transfer on the string interface, but only certain byte has a valid data, and you use the keep. Yeah. And then scope, that means I want to read how many data I have valid data. Yeah. And user and the ID is used for the routing. Yeah. For example, I have a string switch. If I have a switch, then you have many different producer. You have a different consumer. One. You have another consumer here. You have another producer here. Each one has an ID. Okay, producer has an ID and consumer has an ID. So you can specify using the ID signal to tell the switch how to direct the data. You can have a producer address the ID 1, then it comes to this consumer, and different ID to different consumer. Okay. So that's the use for the ID. Yeah. And when you write the code, you can use the this template or using the HLS provide all those. These two are actually the same. Yeah. In here, APXIS and this APXIU, that's a signed integer, and this unsigned integer here. Yeah, this unsigned integer, and this signed integer. Yeah. So you can pull on a different data type. Yeah. In here, the data type you use this one, and you can also have the data type for structure. Okay. So you can, for the string channel, you can have all different type. You can also aggregate multiple variable into one string. It's all depend on how you declare the data type. The data type here. Okay, so that's a string interface. Okay, for certain timing consideration, sometimes we want to register the interface. Yeah, so you can put the pipeline register either on the forward path or reverse path or both direction. Yeah, so for this one, that's the channel from producer to consumer. Okay, so you can put the pipeline here. Okay, so forward path, the T data, T value. Okay, that's the forward path. Yeah, the T data and value signal we put on the register. And for if reverse, that will be the ready signal. Yeah, you put the register here. So this one, virtually you add the actual pipeline stage. It gives you better timing, but longer latency. Yeah. So whether you want to put the register depends on the timing report and see if the string interface has a timing select. Yeah. In that case, then you optional put the register. You don't always put on that because increase the resource usage because register takes up resource. You also increase the latency. Yeah. So you use the register interface only if it's necessary. Okay, let's talk about the string interface, and that's a very handy tool. Okay, there's a Xilinx provide APFifo string switch. Okay, so and all the IP, the input and output is using the string interface. So it provides a very easy way to compose the pipeline design. Okay, so for example, like here, you can design a very suppose this is a smart camera. Okay, smart camera. So you have a camera in the front end and HDMI input. Then you do the necessary image processing. Okay, so let's say that I want to do the object detection. Okay, or I want to do defect detection for whatever things that operate on the image. So you can have a existing image input and output. And I want to do the AI model to do the defect detection. Then, for example, I put the neural network here. Okay. Then you can use the switch and redirect this one input to this one. And then you can output after processing and then get back to the original image stream. Yeah. So you use this way, you can use software. All those things, it's just, you can do all this in software. Yeah, and just write the code, the C code, and code the necessary functions, and hook them up together, and then automatically compose the whole system design, and then you can put into the FPGA, and very, very convenient. Yeah. Okay. And also for this certain part of design is static. Remember the FPGA, we can do the partial programming. That means inside the FPGA, you don't need to load the bit string for the whole FPGA at one time. Yeah. For example, this FPGA, you have a PCIe interface. Talk to the host. Okay. And this FPGA at the runtime is still running. And you want to update certain function. Yeah. And other part is the fixed part. For example, for the PCIe, you cannot reprogram PCIe. Once you reprogram PCIe, you disconnect from the host. The system break, right? The system is still running. The PCIe is still doing the transfer. Yeah. But you can update the function for certain region. Yeah. For example, at the runtime, I want to change another neural network. Okay, you can load it into that, and the system is still running. Yeah, that's called partial programming. Yeah, so that's what this part, that there are certain static part here. Okay, and then there are certain part that you can swap in, yeah, your bit string. And since the region is small, then the stream, the bit string upload is very fast. So the latency is short. So that you can do these things while the system is still running. Okay, so this is a composable pipeline. Yeah. Okay, so that's thing I like to talk about. I keep saying that the host and kernel communication through the XI light and this remember this one using the XI the AP control handshake, or even though I want to do pipeline, then I can use the AP control chain, right? You learn this too, and this one is better, give you pipeline, but it's still not good enough. It's still not good enough because you still need to use the memory map I/O to control the block. Okay, so what you really want to do is using the XI stream. Okay, that means you have a host program, and you have a kernel function. Okay, and the kernel function interface with the host is not through the XI Lite, not using this one. I want to use XIS using the string. Okay, without any other handshake protocol. Yeah. As I said, for doing that, I need to use the QDMA. Okay, so the host can do the memory map, directly write the data to the string. Okay, so once you write in and also the data, for example, this kernel function that has a certain argument. There's an argument, certain argument. Yeah. To have this kernel function running, you have to fill in the argument. Okay, and a certain small amount of data. You use the memory map IO and write into the string. So when it's detected it's not empty, the kernel can start running. Yeah. So it's much more efficient than using the AP control handshake or AP control check. Yeah. For this one, there are certain application, yeah, already using that. Yeah. And like the high frequency trading, there is another platform for the high frequency trading. They are upgrade to using this protocol because for the host, it's running the strategy. Yeah, and the kernel function doing all the network processing, TCP/IP network processing, and there's like the older book, all those things. Yeah, and the way to the host, because it needs very low latency. So when the strategy compute the cell, the bit of cell order, then it can directly write the packet out instead of program the kernel function, then get the data from system memory. Yeah, will be very slow. Yeah. So we see for those very latency critical application, yeah, people like to use host and kernel using the string interface. Yeah, it save the the kernel synchronization overhead. Okay. At last, the question, yeah. First one, what port is used to specify port level protocol? Answer. Yeah. Okay, the second question, I think the answer is the return. We use the port. We use the port return. Yeah. Specify the block level protocol. Yeah. What is the interface used for host to program kernel configuration? A, B, C, D. C, XI Okay. For kernel to directly access host memory, what interface we often use? Yeah. So either the XI master or use the XI string. Yeah. We probably won't use the XI Lite. Yeah. Because you can still return the data. Remember the AP return. Yeah. The return actually is saved in the XI Lite register. But we won't use that because it's very, very inefficient. Because you have to, the software have to come to read it. Yeah. Instead of the data sent to the system memory. Because you want to use the DMA for the kernel function to transfer data to system memory because the whole CPU will read much faster. Yeah, if a whole CPU has to come to the XI Lite, come to the I/O to read the data, it will be too slow, right? Yeah, so you want the kernel function write the result to the system memory directly. Yeah, even better is write to the CPU cache. It's even faster, right? Yeah. Okay. Question. XI slave, that's right to the directly right to the global memory in the kernel in the FPGA side. Yeah. So we can use XI. You can use the XI Lite core or XI slave. If the the memory is big chunk, it's overflow because XI Lite the address space is limited to 64K. I remember 64K. If you want to allocate bigger buffer, data buffer, and the buffer you want the CPU to fill the data instead of using DMA. then you use a XI slave. Yeah, let the CPU fill the data. Yeah, I didn't talk about XI slave because rarely use it. Yeah, no any benefit to you. Okay, so it's about today's course. Mm-hmm. Oh, Yilin, yes.
Oh, so I have a question. So, is
要不要
exile
stop?
slave is for the master to talk to communicate with the slave or kernel, something like that? Is
Master, you mean the master is a kernel, right?
the master like So isn't the master means the CPU, the host?
Okay, when you say master, normally we say it's kernel. If it's host, you say host.
Oh, okay.
Because otherwise
Then,
it's confusing. So you
Uh,
are talking about host or the kernel master?
I'm sorry, Professor, your voice is not very clear.
Oh,
Oh,
yes, I
yeah.
can.
Okay, I can
Oh,
hear
my
you
God.
now.
Okay, okay. So you mean it's a host or it's a kernel master?
Oh, I mean the host.
Oh, the host. Okay, okay. Then what's your question?
Oh, so it's AXI slave is the host talking to the kernel.
Right,
AXI 4, AXI slave 4.
right. Yes. Wait. Exile slave. Exile slave. That I probably confused. I need to come back to see this one. Mm. Yeah, slave. Yeah, normally the slave is a kernel size slave, right? Yeah.
So it's kernel to
No,
what
XI slave. That means the whole CPU. That means the kernel function is a XI slave, like a XI lite.
Oh, oh. So
Okay,
in this
XI
case,
slave. That is it becomes a memory slave. So it write to the kernel global memory.
oh, so XI is for the host to write to the local memory in the kernel.
Yes, yes.
Oh, okay, okay. So in this case, the kernel is the slave.
The kernel is slave. Yeah, it's a memory slave.
So the kernel can be the master or be the slave.
Right. Yeah. Kernel as a master means it's the XI master. It initiate the transaction and transfer the data to system memory. So at that time, the host memory is a slave, a memory slave.
Oh, so the master depends on who initiate this protocol.
Right. Yes.
Okay, okay, then I get it. Thank you.
Okay. Yes. Okay. Yeah. So any more questions? Yeah. Hopefully, I think the I/O interface is a big part of the HLS. Yeah. Hopefully, you have a very clear idea what kind of interface you can use to communicate or doing the kernel interface. Yeah. And next week we will talk about the pipeline and data flow. That's the major part of the HLS. Yeah. Okay. Yeah. If no further question, yeah. So we will end the class today. Yeah. Okay. Yeah. Thank you. Yeah. Bye bye.